Welcome to Physics 371 Online. Today I'll give a brief overview of a new piece of mathematical apparatus that we find use for especially in electricity and magnetism in physics, and that's called the Dirac delta function. The basic reason that we define this kind of a mathematical tool is that sometimes in the world we encounter quantities that have interesting combination of properties. They have a fixed amount of stuff, but they exist at a single point in space, which means that their volume is zero. And yet, they carry a fixed amount of mass or charge. For example, think of an electron at a certain point in space. It has a finite mass and a finite charge, and yet the mass and charge are at a single point, at least as far as we know. And so, if we wanted to write down a function for the mass density, which is the mass per unit volume of a point particle, let's call it rho. What we would see is that rho, as a function of space, would have to have the property that at one single point where the particle is located, it would have to be infinite, because mass per unit volume, well, there's a finite mass and a zero volume, so that would go to infinity, but that everywhere else in space it would be zero. At the same time, then, this function would have to have the property that if we integrate the mass per unit volume, over all space, we would get the total mass, which is finite. And so this is an interesting property. What kind of a function has those properties? The way we handle it is by defining this quantity delta of x, which is the Dirac delta function, which, for definitional purposes, we say has an infinite value at a single point in space. And here, if we write it as delta of x, the point in space where we have the singularity is the point that makes the argument equal to 0. So at x equals 0, the function goes to infinity. When x is not 0, it's 0. And then integrating over all values of x for this one-dimensional function gives us 1. So just for graphical purposes, on an xy axis we would plot delta of x, and it would be a very sharp spike, much sharper than I'm actually indicating here with this green curve. So it goes toward infinity at x equals 0 and then tails off to 0 everywhere else. So this is purely an artist's conception to show that it's actually there. It's so narrow that we actually would not be able to see it. And something worth thinking about is what are the dimensions of delta of x? And that should be apparent by looking at this integral. Because if the integral of delta of x times a length element dx is equal to 1, and if that 1 is dimensionless, then delta actually has to have dimensions of 1 over length. Another consequence of defining the delta function this way is that if we multiply the delta function by another function f of x, we can take that product and replace it by simply the value of the function at the singularity times the delta function. And that's because the delta function is 0 everywhere except for the singular point. And so we can forget about all the other values of x at which this function might be defined and only write this as f at point 0. And a way of thinking about this is that multiplying a function by the delta function picks out the value that it has at the singularity. So if we were to take that product now and integrate it over all values of x, you could replace f of x by f of 0 using the property that we just mentioned, and then that would simply be a constant value that would come outside the integral, leaving behind the integral of delta of x dx, which we already know is 1. So we would simply get the value of the function at x equals 0. Now something else we can do, if the delta function is going to be used to represent something that's not at the origin, but as at some other place on the x-axis, let's say x equals a, we can simply shift the argument. So delta of x minus a is a delta function where the singular point is at x equal to a, the value of x that makes the argument be 0. And therefore, if we multiply this delta of x minus a by a function f of x, what we pick out is the value of the function at x equals a. So integrating then, we would pull out this f of a outside the integral, and we would simply get f at point a. Here's an example using some of these properties for an expression involving a one-dimensional delta function. What would you make of this expression? 9x squared delta of x minus 3 dx integrated over all values of x. So the first thing that you would do is make use of the property up here so that multiplying 9x squared by delta of x minus 3 would only have a non-zero value where x is equal to 3. So the first step would be to plug in x equals 3 here, and that would give you 9 times 3 squared, which is, of course, 81, and that can come outside the integral. So we now have 81, and what's left is simply the integral of the delta function, x minus 3 dx, over all values of x. And the only thing you have to think about here is to make sure that the domain of integration includes the singular point. As long as it includes x equals 3, then this integral will become 1, and we just get 81 as the answer. But you have to be careful, because there could be cases, like this one. What if we integrated exactly that same function, but we integrated it over the domain from x equals negative 5 to plus 2? Quick inspection shows that that region does not include the singular point, and therefore the value of f of x at all of those different values of x would simply be 0. And so we would get 0 here. The delta function kills off this function if the domain of integration does not include the singular point. One more special property of delta functions can be easily derived by imagining that we have an expression delta of some constant k times x. And what that k really does is it changes the width of the delta function in a kind of an interesting way. So in order to evaluate this, let's first do a variable substitution. So we'll take the integral that involves some general function f of x times delta of kx, and we're going to let y equal to kx, so that dx would be 1 over k dy. And now we'll substitute both of these into the integral. So that will leave us with, the integral will be, well, delta of kx becomes delta of y, and then dx becomes dy over k. So 1 over k comes outside, and we're left with the functional value at y over 4. The domain of integration is the same for both x and y because they're only different by a constant. So the integral still runs from negative infinity to infinity. So what do we do with this? Well, the singular point is at y equals 0, so we plug in f of 0 over 4, or just f of 0. And the f of 0 can come outside the integral along with the 1 over k, leaving behind the familiar integral delta of y dy. And I know that's equal to 1, but I'm just going to leave it like this for a moment, because the way that we will evaluate this expression delta of kx is by comparing this result to another result that we could obtain directly from the original integral. F of x delta of kx, well, the singularity is at x equals 0, so this is also, it's also possible to write this as f of 0 delta of kx dx. The f of 0 comes outside the integral, leaving behind integral of delta of kx dx, and we can look at this and see that both of these two expressions, the one from the previous line and the one from the lower line, they both must be equal to each other. They came from the same initial expression. And so that tells us that there must be a very simple relationship between delta of kx and delta of y. So by inspection, we see that delta of kx must be the same as 1 over k times delta of x. Even though the expression in the top line has a y in it, we could write it just as easily delta of x dx. It wouldn't change the expression at all. So when you have delta of kx, you're actually narrowing the distribution, in other words, by dividing it by a certain number. And you can show more generally that whether that number k is positive or negative does not affect the final answer. So if k were to be negative, you would just take the absolute value, and that would give you a way of expressing delta of kx. So this property may come in handy at some points. Finally, the Dirac delta function is often expressed for a three-dimensional world because these particles, like electrons that we find, exist in 3 dimensions. And we can define a three-dimensional Dirac delta function using this notation, delta cubed of r vector as the product of the three delta functions for the three coordinate directions. Here in a Cartesian system, it would be delta of x, delta of y, delta of z, and it has the familiar property that it's equal to infinity at the origin, where these three are all 0, and it's equal to 0 everywhere else. Of course, to be consistent, we'd want to have the property that the integral of this delta function integrated over all space would simply be 1. And so that's indeed what we have. So what are the dimensions of delta cubed of r? Using the same line of reasoning that I did a few minutes ago, you can see that what you're integrating, delta cubed of r, is being multiplied by a volume element here, to get a number, a pure number. And so it's clear that delta cubed of r must have dimensions of 1 over volume. Finally, then, just as we did for a one-dimensional Dirac delta function, we can multiply this three-dimensional Dirac delta function, which has its singularity at r equals r0, some specific point in space, multiply that by a general function f of r, and it picks out the value of f of r at the singularity, at r equals r0. And we can use that then to evaluate the same kind of integral that we did before for a one-dimensional function, and we see that that integral, of course, picks out the value of the function at the point where the singularity exists. So that's an overview of the Dirac delta function. Homework problems will give you some practice evaluating expressions that have these, and I'll also give a little bit more motivation in class for a specific kind of function about why the use of the Dirac delta function can help us solve certain kind of paradoxes that seem to occur when we're dealing with some kind of vector functions. I'll see you in class.